All right, we're working related rate problems, and of course we're starting off with some fairly simple stuff here. So we're always going to start off with an equation, and then they're going to ask us, right, to find something. For example, we're going to find dy over dt, and then we're going to be given some information over here. And this time I'm going to be using some units, centimeters over seconds. So this should look familiar to you. X squared plus y squared is equal to 16. We want to find dy over dt. And when dx over dt is equal to 4 centimeters per second, and x is equal to 3 centimeters. So first thing we're going to do is we're going to take this, and we're going to take the derivative of it, each one of these variables with respect to t. So we take the derivative of x squared and you get 2x, and then we tack on this dx over dt, plus we take the derivative of y squared, which is 2y, and we tack on dy over dt, and of course the derivative of 16 is 0. So we want to find dy over dt. Well, here's our dy over dt. We need to plug in a y, plug in for x, and then solve for dy over dt. Well, let's see what they give us over here. They give us a dx over dt, so we're going to plug 4 into here. And then they give us an x, which is 3, and then we'll put 3 in here. But what they don't give us is a y. So where in the heck are we going to find that at? Well, we can come right back up here to our original equation and just do that. We can solve for y in here by taking this x right here, which is a 3, plugging it in, and then solving for y. So then we'll have our y. So then we can plug our y in and then just go ahead and solve for dy over dt. And we'll talk about this, what's going on over here on the right hand side here in a minute. So we're plugging in for x right here, and then we're going to solve for y. So it looks like y happens to be the square root of 7 after you solve for y, right? 9, take it over to the right hand side, 16 minus 9, and then take the square root of both sides to get rid of this square. Alright, you get square root of 7. And then what we're going to do is, so I went ahead and plugged in up here, what's going on up here if you're wondering. I went ahead and plugged in our x, then plugged in our dx over dt, and I hadn't quite plugged in our y yet, but I think we're going to do that right down here below. Okay, we took the square root of 7 and we plugged it in right here, and now all we got to do is some algebra and solve for dy over dt. Taking the 24 over to the right hand side makes it a negative 24, and then dividing both sides by 2 over the square root of 7, as you can see here. And then we need to simplify this down. So we simplify it down, and if you notice now here at the end I've thrown my units in. So since we were started with our units of centimeters per second, we need to go ahead and put those in now. So it's kind of hard to judge what in the world is this, right? Well, I went ahead and just approximated it to 2 decimal places like I normally do, just approximate to 2 decimal places. No real reason why 2 decimal places, I just chose 2 decimal places. Alright, so it's, and that actually should be negative right there. Let's change that. Okay, went ahead and made that change, so that's a negative 4.54 centimeters per second. Alright, well, in this part of the problem here, which is extra, I'd have to say, what I've done here is, as you can see, the y that normally is right here, I replaced it with the square root of 16 minus x squared. And remember up there in our original, x squared plus y squared was equal to 16. I went ahead and solved for y in that equation. And so now what we are going to have is we're going to have something that's more general here. And that is, we're going to have this equation here so that when we plug in some x value, we can see what dy over dt is, right, for some x value. So it's just a more general setting. And let's see what I do down here. Alright, so I went ahead and solved for dy over dt by taking the 8x over to the right hand side, which is a 4x. But when I divided both sides by 2 over the square root of 16 minus x2, 2 goes into 8 4 times, right? Just simplifying it down. So we've simplified this down now. Now we've got a function here of y, or the rate of y, I guess I'd say with respect to time, as a function of x. And so now we can actually just start plugging some x values in and kind of looking at what does dy over dt do, right? So we looked at when dx over dt was 4 centimeters per second, and that's kind of what we're sticking with in here. But it's the x that's going to be changing. The x is changing. And so if I let x be 1 centimeter, then dy over dt is negative 1.03 centimeters per second. Right, and so we plug 2 into this and we get negative, dy over dt is negative 2.31 centimeters per second. So it looks like it's speeding up. Remember, the negative tells you the direction that your dy over dt is going towards, and it's heading towards the x-axis actually in this particular case. What in the world is this? X is equal to 2.83. Well, I think this is a special number because this is where dy over dt, and I've got an approximate sign right here because I just approximated it here to 2 decimal places, so we must put an approximate sign here. But this is where they're pretty much equal, right here when x is equal to 2.83. So I thought that was really kind of interesting. And then, of course, we're looking at 3 centimeters, and as you can see, it's speeding up more. And so we got negative 4.54 centimeters per second. Now, I graphed this out to kind of look at the graph instead of just kind of, looking at some values here. But I've got a graph here. I don't know what kind of help it's going to do, but let's take a look at it. Okay, so along this axis here, this is our dy over dt, and then this is x right here. So it looks like it really kind of curves up right here. It seems like it's kind of straight and then kind of curves up right here. But you can tell a lot by looking at a graph, right? So this would be 2. We would come up, right, read straight across, and kind of get an idea of what our dy over dt is. But it really kind of speeds up going here. Well, because we have, it seems like we have some kind of vertical asymptote going on here. All right, I think I was, phone rang, had to put it on pause, and now I've forgotten where I'm at. Okay, anyway, I mentioned something about a vertical asymptote, but remember that we can't have negative, right, up underneath the radical here, so we can't be putting anything greater than 16 in down here. Because if we put 16 in, as if x were 16, right, we'd end up getting 0, and you can't divide by 0. But what's actually interesting here, and I don't have it actually written out, is if we took the limit of this as x approached infinity coming in from the left-hand side of 4. I didn't mean if x were 4, not x were 16, right, because 4 squared is 16. But if we're coming in from the left-hand side of 4, if we took the limit as x approached 4 coming in from the left-hand side, you would see that this limit would actually go to positive infinity, which means that it's increasing. But which is kind of interesting, and I don't have that actually written out here, and I probably should. But let's look at the the graph of the original function. Okay, so here's the picture that we were looking at. This is the graph of x squared plus y squared, which is equal to 16. Now, of course, that's the graph of a circle. And, of course, we're only looking at between 0 and 4. We're only concerned about what's going on over here. So here's a point, and if you can think of this point actually as moving along, right, this path. So this is a point moving along this path right here. And of course, remember this arrow right here means that it's, what is the point doing as it moves in the x direction, and how fast is the point moving in the y direction. And this was at x equals 3 centimeters. And of course, this was our centimeters, measured in centimeters here, and so forth.